Hi students, welcome to week 3, and this week we're covering 8.5 and 8.6. In this video I'm going to go through 8.5 and in the next video I'll go through 8.6. So I'm going to introduce you to Le Chatelier's principle, and you should have already heard about this through Ed Rollo. You should also be looking at the textbook yourself. But Le Chatelier's principle I'm also going to refer to as LCP. So LCP. So Le Chatelier's principle, or LCT, states that if an equilibrium system is subjected to a change, the system will adjust itself to partially oppose the effect of the change. So what's that saying is whatever change is put into a system or put into a reaction, it's going to try and do something. So it's going to try and oppose, go in the opposite way of the change. So the three factors that can disturb equilibrium are over here. So there's the addition or removal of products and reactants, changes in temperature, and changes in volume or pressure. Okay, we're just going to look at this one. So the addition or removal of products and reactants. If I have an equation A plus B to give C. Okay, if I add a reactant, so I add A, that means I'm going to have a lot of reactants. It's going to make more products. It's going to shift to the right. By adding a reactant, add A, or I could have added B, but it's going to make more C because I've now got too many reactants. Okay, and just a reminder, here are the reactants. Reactants are over here on the left-hand side and products are on the right-hand side. Okay, if I add a product, it's going to shift to the left. If I add C, it's going to shift to the left. Why? Because now I've got too many products. If I add a product, I've got too many products and it's going to want to go back to equilibrium, and so you're going to have a reverse reaction and produce more reactants. Okay, so let's be clear again. If I add reactants, it's going to make more products. If I add products, it's going to make more reactants. Okay, this looks scary, but let's just unpack it. So this is from your textbook. Now, this graph is a rate time graph showing the events that occur as a mixture of nitrogen and hydrogen gas returns to equilibrium after the addition of extra nitrogen gas. Okay, so let's highlight the reaction. So currently, what it looks like is that this system, so the reaction of nitrogen and hydrogen to produce ammonia, is in equilibrium because the rates of the forward and reverse reaction are equal. So it's at equilibrium. Yeah. Now what happens here? Increased concentration of nitrogen gas. So they've added nitrogen gas here. Causes more frequent collisions to occur between nitrogen and hydrogen molecules, producing more ammonia. The rate of the forward reaction infinitely increases. Okay, so we've added nitrogen, and now the forward reaction is increasing. Okay, so the forward reaction increases, and the forward reaction is the instant increase is this sharp vertical line. And what happens as the concentration of ammonia increases and more frequent collisions occur between ammonia molecules, the rate of the reverse reaction to reform nitrogen-hydrogen increases. So this is the reverse reaction. And that increases because you're producing more ammonia. You're producing more ammonia over here. Or it's better to say you're producing more ammonia, so the reverse reaction is happening. Here, you've added a lot of nitrogen gas, and that's producing more ammonia, but it's slowing down because you're removing that nitrogen gas. Until you reach a point where the rates of the forward and reverse reactions become equal again and a new equilibrium position is established. So let's just say this is the forward reaction. And then in this period, the forward reaction and the reverse reaction are equal again. So again, it's at equilibrium. Okay. So a representation of, let's go to the next figure. In this, let's see, look at what's happening. So it's concentration by time. Here it was rate by time. If we're looking at concentration, it's at equilibrium here. And then they add nitrogen, and they only add nitrogen at this point because we know that from this sharp increase. And then when they add nitrogen, the nitrogen slowly decreases. So does the hydrogen because it's reacting with the other reactant, so it's nitrogen plus hydrogen. And the concentration of ammonia increases until it reaches equilibrium again. So you can look at these two graphs and kind of compare them. So over here, this is time marker 1, it's at equilibrium. Here is when we add nitrogen, then we reach equilibrium again. Okay, the last figure is a different scenario. So this time, they're adding NH3. At this point, they add NH3, ammonia, and because they have a lot of products, the products collide with each other, and the reverse reaction will be favoured, and nitrogen and hydrogen will be produced. Have a look at these questions, and these are the questions that you're required to also complete. Let's just look at a couple. So we'll look at 1A. So use Le Chatelier's principle to predict the effect of adding more hydrogen gas to the following equilibria. So if I add hydrogen gas here, that means I'm going to have a lot of reactants. More reactants, which means that reactants will react and give me more products. So therefore, shift is to the right, and therefore it is the forward reaction. Okay, let's look at another question. To A, predict the effect of the following changes on the position of each equilibrium. Addition of SO3 to the equilibrium here. Okay, so again, if I add SO3 is, so I'm going to write here, add SO3, that means it will be more product, because SO3 is a product, which results in more reactant, which is actually a shift to the left, and then that results in the reverse reaction. Okay, and let's just do part of question 3. For each of the equilibrium systems in question 2, explain your answer by referring to the mathematical expression for the equilibrium law for the system. So we're going to just refer to 2A. So let's write the equilibrium constant, which is SO3 divided by SO2 and oxygen. Now, if we, sorry, there's a fly in my face. If we add SO3, that means this will increase. If this increases, that means the number, or K, will also increase, which will mean Q will be greater than K, and therefore the reverse reaction needs to happen. Okay, I hope that makes sense, and I'll see you in the next video.